Okay, I think we can start because we are like 3 people speaking, although we are going to try to keep it as short as possible. But I'm going to start with the introduction. I'm not going to only introduce our 2 speakers today. I will do it later. But before, I wanted to say something about what the GATOS collaboration means and where we come from, because I think it can be useful for the IC people, because some of you may not know it. And also for our GATOS juniors members who might not know all the story behind the GATOS collaboration, no? And I thought it was like important to do it because somehow GATOS was born here, no? And well, let me explain. Here in the Canary Islands. So, what happened? Oh my God. Shall I start again or do I continue? Okay. Okay, so as I was saying, GATOS, which is now an international collaboration of nearly 60 researchers, comes from the Canary Camp AGN science team that we were called Los Piratas, because the name was proposed by one of our British members, Chris Packham. So he created and formed this team, the Canary Camp AGN science team, to maximize the scientific return from the Canary Camp guaranteed time observations. When Canary Camp, for those of you who don't know it, was a mid-infrared instrument on the GTC. It was operating for several years, but now it's no longer there. So like I said, we have this guaranteed time observations of nearby AGN, and Chris put together a team of researchers to work on this data. And thanks to this very nice collaboration, we also were awarded an ESO GTC proposal to observe more AGN with Canary Camp, no? And this was a proposal led by Almudena Alonso Herrero, who is another of our team and board members. So our aim was to investigate this nearby AGN to understand the role that the nuclear activity played on the Torus, which is this obscuring structure that the galactic nuclei have, and also surrounding star formation and the host galaxy in general. So this is a picture from one of our Piratas meetings here in La Laguna, if I remember correctly, taken in 2014, although I'm not completely sure about the year. So the survey that we managed to put together, like linking the guaranteed time observations and also those from this ESO GTC large program, covered nearly 50 AGN, nearby AGN, covering more than 4 orders of magnitude, and including different AGN types. And the Atlas paper was published by Almudena herself in 2016. And we got mid-infrared imaging into filters and also low-res spectroscopy in the end band and sample arimetry of interesting objects. And one of the key achievements, something that helped us getting all the scientific return from this data from Canary Camp, not only for Los Piratas, but for the whole community, was the development of RedCan, which is the pipeline that we use to reduce the imaging and spectroscopy data. And that was like fully developed by Omaira Gonzalez Martin, who is also here today with us. And she was a postdoc here at the IAC at the time. And she not only developed the pipeline, but she published this nice paper in 2013 analyzing the nuclear spectra of this nearby AGN and comparing them with Spitzer to characterize the dust properties of this nearby AGN. So these are some of the old pics from Los Piratas. We were meeting mostly in Mexico and Florida and here in the Canary Islands. because these are the partners of GTC, and you can see some like a very younger version of ourselves, no, like back then. I'm not sure if I should have included them. One of the milestones of Los Piratas, we published, for example, the first Canary Camp paper, also by Almudena in 2013, studying this system of dual AGN, one of them really obscured by nuclear dust. And so that was a letter that we published. And we also made an important contribution to the study of obscuration in AGN, using Canary Camp data, but also mid-infrared data from Gemini instruments before we had the Canary Camp ready at the GTC. So we published a lot of papers on this characterization of the torus, of this nuclear dust that is obscuring the central region of AGN, using SED fitting, so fitting the photometry of this nearby AGN with different torus models to try and investigate which were the properties and how they depended on things like AGN luminosity, type, etc. And I would like to emphasize also that several PhD theses were done totally or partly based on Canary Camp data. One of them, for example, by Enrique López Rodríguez, who is also here, and he was a grad student here in Tenerife, but then he did the PhD in Florida with Chris Packham, and he studied these polarimetric observations that we get from Canary Camp to characterize the different contributors to this polarization signal that we measure in this AGN, like, for example, here, Cygnus A. Then we have the thesis of Mariela Martinez Paredes. This thesis was done at the INAOE in Mexico, supervised by Itziar Arechaga and Almudena Alonso Herrero. And her work was very interesting because she was looking at the pH features, which are these features that we use to characterize star formation, recent star formation. So she was looking for these signatures, these features in the spectrum of nearby quasars to see if at these high luminosities, these pH features were observed. And she found evidence for them in the central region of some of these quasars, which was very interesting, no? And we still continue doing these studies now with James Webb. Another PhD was by Judith Garcia Gonzalez, she did a PhD in Santander, supervised by Almudena. And this was only a small part of her thesis, but she used the Canary Camp data to test new torus models that were developed by also team members, in this case, Sebastian Hoenig, to see if with the data, we could put more constraints and refine the geometry and the properties of the dust of these models. And finally, the thesis of Ismael García Bernete, one of our speakers today, who I supervise together with Jose Acosta here at the IAC. And his PhD work was completely based on mid-infrared data from Canary Camp, but also from Gemini instruments, as well as Spitzer. And Ismael characterized the nuclear and extended mid-infrared emission of a sample of Seyfert galaxies. And we put constraints on the nature of the extended emission. We also use the nuclear emission to test these torus models. And yeah, he defended his PhD in 2017. So now, so this is the story behind GATOS. We were Los Piratas for a few years, and we were very successful in using this mid-infrared data from ground-based telescopes. But in 2016, we met in Madrid. We invited other people who were working also in mid-infrared observations, but were not our colleagues at the time. So we got them together. We tried to join forces in order to understand nuclear activity in these nearby galaxies. And since 2016, we became GATOS, partly because we were in Madrid, and people from Madrid are called GATOS as well. But the name is Galaxy Activity Torus and Outflow Survey. And like I said at the beginning, now we are 60 researchers from different institutions around the world. This is the science board, and we have met several times. These are two examples of meetings that we had here in La Laguna back in 2019 and in Madrid last year. So this is today we start our, I think, fourth GATOS in-person meeting. And we have been really successful. For example, getting James Webb observations. We have been awarded 9 proposals with James Webb, which tells you a bit about the importance of the work that we are doing, I believe. And this is what today Ismael and Steph are going to summarize here in this seminar for us. We thought it would be nice as a way to thank the IAC for hosting us this week, because we are going to be disturbing a little bit the life in the center for the week. And so I leave the floor to them. But before, I would like to introduce them. Well, Ismael, as I said, he did the PhD here at the IAC, and then he moved to Santander as a postdoc, and then he moved to Oxford to work in the group of Dimitra Rigopoulou, and he was there 5 years. And now he's in Madrid with one Atracción de Talento fellowship. And Steph, she did the PhD at St. Andrews in the UK, and then she moved to not very far away to the University of Newcastle, she's a postdoc working on GATOS observations, and the two of them are board members of the GATOS collaboration. So today they were kind enough to take the responsibility of telling you of all the work that we are doing within the collaboration based on this James Webb proposal. No? So thank you both for doing this. Okay.
Hello. Let me put some time so I can divide this for Steph and myself. No, okay. Okay, hello everyone. Thank you. First, I would like to thank you, the organizer, for giving me the opportunity to be here. Indeed, it's quite exciting to be today talking about the GATOS collaboration. I was not long ago a PhD student at DEC. I'm part of the Piratas. So don't tell the security, but I refuse to use this because I feel like that I am at home. So, okay, so today I'm going to talk about the first result that we have from James Webb in the GATOS collaboration. I'm going to focus on the MRS, and Steph is going to talk on the imaging side. So before starting, I would like to remind myself why all of this is important. Why do we care about active galaxies? Why do we care about dust? And why do we care about the infrared? So I'm not going to spend much time here, but active galaxies are galaxies that have supermassive black hole that is accreting material. And this nuclear activity is indeed one of the key elements on the galaxy evolution. So these galaxies, active galaxies, were thought to be just 10% of the galaxies, but we know now that they are not considered weirdos anymore. They are a short but recurrent phase on the overall life of galaxies. So this active phase is indeed a very important phase on the evolution of galaxies. Okay, so these AGNs not only accrete material, but also produce some feedback, what we call feedback. This feedback can be multi-scale and multi-phase. So we can see this feedback in the innermost region where most of the action is taking place, but we can also see this feedback at galaxy scale and even larger than that when we have a strong AGN. This feedback is, of course, also multi-phase. So we need to have like different wavelength regimes in order to understand very well this AGN feedback and these outflows. So we have still many open questions about these outflows, and this is what we try to answer within the GATOS collaboration. Some of these questions are related with the fact that how the properties of the outflow are related with the properties of the AGN, or how this AGN feedback, negative or positive, is related with the properties of this AGN or the host. No? Some of this work has been already done within the GATOS collaboration. So indeed, let me highlight that ALMA is also a key facility for GATOS, not only James Webb. Indeed, some of these works within with the ALMA facilities has been led by Santi, our ALMA guru. He has been working in many different works, but I would like to highlight this one, what I think that is quite important. He used a large sample of galaxies running from low luminosity AGN to cipher luminosities. He found that indeed the AGN feedback make a strong AGN imprint in the molecular gas that is very close to the nuclear regions. In this imprint can be seen in a trend that depends on the volumetric luminosity of the AGN and also in the Eddington ratios. So this work has been extended for larger sample by Santi, and also Fede very recently is looking at this using the clumpiness of this molecular gas. So Santi also worked in the ALMA data to resolve the torus. The torus is indeed the key element of the AGN unification model. This optically thick dusty torus, according to the unification model, depending on the orientation of this torus, we are going to have a type 1 or type 2 AGN, no? Depending if we have a direct view of the central mechanism or not. We know now that this is much more complex, that the dust is clamping this, so we can have a direct view even if you are not face on. But we have also a torus that is very small, difficult to resolve, and we have plenty of dust that is not only located in the torus. We have dust that can be in the polar direction, in the narrow light region, and so on. So anyway, depending on how this dust is distributed, we have this dust is going to absorb part of the intrinsic radiation of the AGN and is going to remit it in the mid-infrared. So the mid-infrared is key for us to understand these dusty regions. We have many open questions related with the torus, indeed. So we don't know how these properties of the torus depend with the AGN properties. We have some hints with previous work, but we would like to understand this better in a large sample with very high angular resolution. We would like to understand if this polar dust that we see in the polar direction is related with a dusty wind, indeed. We would like to know the molecular content that we have in this torus, because if we have plenty of dust and molecule come together, so we should have a rich molecule environment. Is dust only important for the nuclear region of AGN? It's not the case, no? So if you have a look in the optical to a galaxy in the extended region, this is the view that you have from Hubble of a very beautiful spiral. So you will see all the gas here, and you can see some of these regions that are dusty and are very obscure. Also in the nuclear region gets very blurry or difficult to see because we have a lot of extinction in the optical. Now if you have a look in James Webb, what you see is complementary to that. What you have is that you have emission in the region where you have dust here. So this is the regions of dust emitting in the infrared. And then in the nuclear region, you have a more clear view because you have less extinction. Of course, if you would like to understand all of this, what you would like to do is combine as many wavelengths as you can, no? Okay, so that is very important for us, and that is emitting in the mid-infrared. So the mid-infrared indeed is very interesting for us, not only because of the continuum that we have, but we have also many different features. So this region from 3 to 30 microns is extremely rich. So we have low and high ionization potential lines. We have H2 lines tracing the warm molecular gas without using any conversion factor. We have polycyclic aromatic hydrocarbons, what I am going to call PAHs. For the sake of simplicity, they can be aromatic or aliphatics. Never mind, they are going to produce these infrared bands. No? We have also some features that are coming from the dust, like the silicates, and we have many other molecules that are going to produce features in the gas phase. Okay, so let me just spend 1 minute introducing PAHs. So PAHs are carbon-based molecules. They are very interesting for us because they absorb UV photons from the star and remit it in the mid-infrared. And the very nice thing of these molecules is that they produce different bands, and all of them are very bright, but really bright. If you have a look to this histogram, you are going to be able to compare with other lines that are very well known. No? For example, H-alpha, you can see here, and the comparison for any of these pH bands is just amazing. No? So these pHs are very bright. So we can use them to detect galaxies that are very faint or galaxies that are very far away. One of the other very nice application of PAHs is that you can use them as a star formation indicator. So you can use, since these are absorbing UV photon, you can use them to trace star formation activity. Also, you can see the different bands in this spectra in red, and you can see in 2 different sources how the relative strength change. So using this relative strength of these bands, you can also use them as an interstellar medium barometer. And also we have found very recently that we can use these pHs to trace the most obscure galaxies in the universe. So we can use them to identify these very obscure galaxies. So this is just to say that pHs are very useful. Okay, so one of the applications for these pHs indeed is to measure star formation rates in the innermost region of AGNs. This is very difficult because at the innermost region of AGN, you have the majority of tracers are contaminated by the AGN, and also we have plenty of material. No? So in principle, the mid-infrared should be a good solution to look for this star formation activity. However, we need to understand if we can use these tracers to trace star formation activity in AGNs. Okay, so I think that I don't need to introduce James Webb, but James Webb is the most complex and powerful telescope that has been ever deployed in the space. Indeed, it's a very complex observatory, so we have like many different observing modes. We are going just to get focused on the MIRI instrument in this talk. And the combination between spectral resolution, angular resolution, and sensitivity is just amazing. Okay, so the first data of this telescope was released in July 2022. But back in the time, we were to the archive and we picked up all the galaxies that were available, and we started to analyze this data. So these are two works led by Miguel and myself. Sorry, but this is the only photo that I found of Miguel and myself together. So this is Miguel feeding Rudolph. Rudolph didn't contribute to this work, but this is myself, and this is in the Arctic. Very nice workshop indeed. Well, this is in the left side. What we have are the pH profiles of these different galaxies. You can see the pH profile of a star forming region, and then comparison with two AGNs and our theoretical models. What we found here is that pHs do survive in the innermost region of AGN. This is a small kind of surprise because we had also some ground observation that was showing this pH is very close to the innermost region. And we found now that since we have all the bands with the high angular resolution, we found that these pH properties are affected by the AGN. No? So the AGN is doing a mess in this population. No? So we can find where the AGN activity is with these pHs. Here, Miguel, what he did is using 7319. This galaxy has a jet, so he tried to understand the connection between the AGN jet and the host galaxy, and he found that the gas can be heated and molecules can be destroyed by this jet indeed. No? This is very nice, but these are just few galaxies. If you want to show some trend or you want to convince people about the stability of this, you need more data. Okay, this is what we did in the GATOS. I think that we were very successful, as Christina was saying before. We started in the cycle 1, we got 2 proposals, MIRI and MIRI imaging. Cycle 2, we got 2 proposals, MIRI and NIRSPEC. Cycle 3, we got other 2, NIRSPEC and MIRI. And cycle 4, we got 3 proposals. So this is 160 hours of James Webb Telescope, what I think that is a lot. It's a lot of work to reduce, it's a lot of results. So now we jump to what we have been doing. So I'm going to restrict this talk to what we have done in the cycle 1, because it's the data that we have already public and the papers that are out. So we have been focusing on, this is the view that we have now for the AGN. I said that the Torus was more complex. This is the kind of complexity that we have. We were working in the ionized and warm molecular gas of outflows. We were also working in Torus modeling and the extra ingredient that we need, this molecular content that we were saying before. We have been working in these pHs, and we have been working also in the nature of the extended emission of this dust. We have been also, we have many other papers that have been submitted and many theoretical and work that is coming from the simulations. And we have been working with many other facilities. I would like to highlight here the GTC, because GTC Megara data has been very useful for us as well. No? So, okay, so I'm going to go now even more quickly for all the work that has been done. So I'm going to spend just one slide per work. So I'm going to focus on MIRI, but within MIRI, I'm going to focus in this bit here. This is medium resolution spectroscopy, this MRS. So data is complex, so we have different channels. Every channel has different sizes, different spatial size, and different angular resolution. This can be a mess. So it is quite challenging to put all of this information together. Okay, so I'm going to start for the sample. This is the sample, 6 galaxies. All of them have similar luminosities and similar distance. This is the sample for cycle 1, which is larger now, but this is the one that I'm going to present here. And the main difference of these galaxies were the outflow rates. Outflow rates were ranging from very low to high outflow rates. Okay, so we have MRS information for all of these galaxies. And we did different studies. No, I'm going to do these blocks here, where we have the ionized and warm molecular gas in outflow first. So I would like to introduce this very nice galaxy. I really like this one. It's my favorite of the sample, 5728. This is work by Rick Davis. We did a beautiful piece of work here. He was looking at the high ionization potential lines, the kinematic of that, to find that the outflow of this galaxy is impacting the galaxy ring and the galaxy disk, so that we have a strong coupling between the AGN outflow, between the AGN outflow and the galaxy disk. He also found, when comparing with ALMA data, that the cold molecular gas was not present, so we had no cold molecular gas in the outflow of this guy. However, looking at the James Webb data, the warm molecular gas is present and is also outflowing there. So H2 is very important for outflows in AGNs. Indeed, he found that this H2 can be explained by slow shocks around 30 kilometers per second. This is a very nice kind of things, because we can use this H2 to trace shocks in these AGNs. So I'm going to jump to the next one. So this is 7172. This work led by Laura. This is another beautiful example. This galaxy has now a very weak coupling. So we have the galaxy almost H4, and we have the outflow like in the perpendicular direction. No? This galaxy also have a nuclear dust lane, making a target that is very difficult to study in the optical, no? Because it's very obscure. Indeed, Laura found that she can detect both sides of the outflow with the mid-infrared observations, and she also found that the outflow properties that were derived from the optical were underestimated. No? Another finding that was very nice in this galaxy is here. I don't know if you can see with this resolution, but these two clumps that are here were related with positive feedback and are in the same direction as the outflow. No? Okay, I'm going to jump to another guy, very different one, NCG05. This is a beautiful work that Donna did. Indeed, this was very, very challenging because this galaxy, this cube, data cube was dominated by the PSF. So Donna did a great job removing all the artifacts in the different apertures and so on. So she found that there are like different clumps of H2 in this galaxy that has no counterpart in the cold molecular gas, and some of them indeed were related with the star formation activity according to the emission of the PAHs. She also found some stratification of the molecular gas. The cold gas measured from ALMA is sitting in the nuclear spiral and nuclear ring. However, the H2 warm molecular gas is filling up all the regions that were empty by the cold molecular gas, which is indeed very, very interesting. So I'm going to jump now to what Lulu was doing with the entire sample. So we have the six galaxies in this study. He did a spatially resolved study where he was using from low to high initiation potential lines. He found that the AGN radio jets may play an important role in driving these high velocity dispersion regions in the observed in the mid-infrared. So this is part of the work. Also, he found very different properties of the outflow when he looked at the mid-infrared compared to the optical. So now we are going to jump to PHs in AGN. As I said before, I think that these features are super interesting in AGNs. What we found here is, as we said before, so AGN is doing an effect on this PA population. Indeed, we found that in the nuclear regions, this is happening in all AGNs. And in this work, what we did is, let's have a look what is going on at larger scales. Is the AGN able to affect these molecules in the outflow direction of these guys? And this is what we show here, where you can see that all the outflow region of these galaxies has different properties in this diagram, no? Telling us that we can use these pHs to trace AGN feedback. In this work by Lulu, he also involved here different ratios of emission lines and photonization and shocks model, and he found hints that we can use these pHs, these properties from the pHs, to trace different AGN feedback modes. So pHs are very useful in AGNs. So the dark side maybe of these findings of the pHs being a good tracer of AGN feedback is that we need to be careful when we use them as a star formation indicator in AGN. So we are going now to move to the solid phase. So these are dust grain and molecular ice mantles. Looking at a first look of the data, what we found is that we have not only the features coming from the dust grains, but we have also some features that are coming from ices. These are the profiles of the galaxy that you can see here of the optical depth, and this is a comparison with the lab data. No? So you can see that the blue region here is mostly able to represent all the profile. However, we have other bits that are not able to be reproduced, and this is because we have extra contribution of other molecules. This is what we call dirty water ices. So indeed, this update our vision of the Torus, because we have now not only the naked grains, but we have also ice mantles in this Torus, no? Making a snow line, as people in the protoplanetary studies call. No? So we have these ices in the outer layer. We found also that these ices are very interesting to estimate the nuclear oscuration. This is important because once you go to very high column density, X-rays are not useful anymore. So you can use these water ices to get these very high column densities. Indeed, we think that we need to introduce all this molecular content in a Torus model in order to be able to reproduce these infrared LCDs. So I'm going to jump now to Torus models indeed. So this is work led by Omaira, very nice work, where she managed to get rid of all the circumnuclear region of these nuclear apertures. Even with James Webb, if you take a nuclear aperture, we get many circumnuclear emissions. So we need to isolate very well the nuclear region. This was critical in this kind of analysis. So Omaira did this job using a different Torus model, and she found that she was able to reproduce mostly the intermediate luminosity ones. However, for low and high luminosity guys, they were not able to be reproduced by this Torus model. So this tells us that we need to still spend some time refining these Torus models. Okay, so a byproduct of this work was this very nice tool. This is a tool that Omaira put together to remove, remember that we were saying that we have a strong PSF. So she made this very nice tool to remove the PSF from the cube. So you have now a cube that is entire PSF, a cube that is entire circumnuclear region. This is very important, and this is done channel by channel in the different cubes. So it is an important job. So this is going to be a very nice tool, not only for the GATOS collaboration, but also for the AGN community in general. So I'm going to stop here and pass the floor to Steph, so she can introduce the amazing.
Thank you very much, Ismail. That was wonderful. It's always really good to see the MRS, and I'm glad that you're the person who describes what MRS data is, because I'm here to talk about imaging data, and that's much nicer because it's just taking pictures. So it's slightly more straightforward to explain, hopefully. No. There we go. So our imaging program was part of cycle 1. It was led by David Rosario, 19 hours. And we were targeting specifically 8 objects. And these were selected based on showing hints of extended mid-infrared emission in ground-based observations thus far. So we looked at them with 5 different broadband filters in MIRI. So MIRI imaging, a lot easier than MRS, we're just taking pictures. But we can see that what MIRI offers us is really good sensitivity and really good resolution. So you can see on the left a comparison of what we're seeing with MIRI on the right and what we used to see with Spitzer. And what we can really pick up are these sort of diffuse areas of emission. And if we are specifically looking for signs here related to dust emission, faint dust emission in the polar regions, this is an ideal instrument to do this. And specifically the bands that we have used, we do have a laser? Yeah, we have a laser. The bands that we've used are tailored so that we can really look at the dust there. So if we look at black body emission with silicate emission in black versus black body emission with star formation in blue, we can see that specifically the 10 micron filter here will really pick up where there's excess silicate emission versus other things going on in our galaxy. So this is perfectly designed so that we can look in our objects and try and find those extended features. And our immediate results, day one, get our images, stitch them together, make RGB images. In here, we would expect dust to appear redder in our false color images. And we can see already hints with very little processing that we've got extended emission in this object. We've got extended emission here. We've got extended emission this way. We've got extended emission over here. So roughly say, with no work, 4 objects already showing this extended mid-infrared emission in the polar direction compared to the Torus in ALMA. And so if we zoom in even more, we can see these extensions. We have extensions here, we have extensions here, here, and up and down this way. Obviously, these images are not ideal. As mentioned in the MRS, we also have a great big PSF right in the middle, which makes this really complex pattern. Straight away from our initial imaging paper, which we have here, we've generated so much work just from this one proposal. We have our imaging sample. We've done work looking at how to model and mitigate this the PSF in 2 different ways. We then have our data product, which are PSF subtracted images. From there, we've been able to look at our extended MIR structures. Looking at shock heating, looking at emission lane contamination in broadband filters, sort of on the more sort of processing side. We're looking at Torus models, similar to Ismail just mentioned, and then we're looking at the properties of this extended dust. So just from our cycle one proposal, we've got a big collection of papers that have all followed on from each other, which is very nice to sort of map out. So first off, we'll start with our PSF treatment. Here it is. This is the Murray PSF. It's horrible. If you have worked with Murray data in any way, I apologize for showing it to you without any warning. Can't really model that with a Gaussian. If you're looking for structures, it's not very nice at all. So we've modeled this. We've looked at mitigating this in 2 different ways. We've used modeling using Webb PSF and subtraction with different scaling. And we've also explored a novel deconvolution technique to do that that way. So with the deconvolution, and this was led by Mason Leist over in the US, this used a novel technique using a software called Kraken, and was partnered with industry partners to deconvolve the image. And what we can see, straight away, we can see that after lots and lots of optimization, we're able to deconvolve the image. We can remove the PSF, we can sharpen the image, and we can recover the nuclear structure here, which would otherwise be sort of entangled with the PSF in the center. This is really cool work. It was really, really interesting to see. And it's being continued by John, who's in the room, to work on removing sort of the crosshair pattern and really refine this method. So I recommend looking at Mason's paper for this. It's a really, really cool piece of work. We also have modeling and subtraction of the PSF. This was led by Mantos Kouraides. I'm a master's student at Newcastle. I don't envy him. He spent most of his master's looking at pictures of the Murray PSF and making it slightly wider or slightly less wide or jitter more or less jitter, to look at how the parameters in Webb PSF are able to best match the observations. Once we can model it well enough, we can scale it and subtract it. So this is our images with the PSF still in there. We're going to do a drum roll. Oh, we can remove them. It's not perfect. We get some over subtraction in the center, but for our science case, which is considering whether looking at the structure of the extensions, we're able to recover those really well. So we can see extensions here in 5728, 3081, and then in ESO 428 and 4388, which are our 2 sort of most striking examples, I'd say. So these 4 straight away by eye show extensions. So we decided to pursue these, and specifically ESO 428 shows really striking extension in the direction of the narrow line region. So our first in-depth study of an object in the sample was led by Huda Haidar at Newcastle, and we focused on ESO 428. The paper here, we looked at the JWST data, but also compared this with HST, ALMA, and Symphony data. And what we managed to demonstrate is that the extension is perpendicular to the torus, so it is polar. We also see that it is aligned with the radio jet and the narrow line region, and is traced by the radio jet strikingly well. And if we estimate and remove the emission line contamination, which I'll speak more about in a second, it persists. So that is down to continuum, which we are going to say is dust. So this isn't down to just emission line in the narrow line region contaminating the broadband filter. This is continuum emission, and it is the same extent as the radio jet in this object. So this is a really cool piece of work. Paper's out there, give it a read. We also, in that paper, looked at the temperature of the dust, and looking at the temperature of the dust and then comparing it to model temperatures for different sources of said dust. We estimated what temperatures we would expect for different grain sizes if it was dust which was illuminated in the NLR, dust that had come from the torus into the NLR, or dust that was heated by shocks. And we find temperatures of 120 Kelvin at a distance of 100 parsecs. And this can only be explained by additional heating from shock processes. We can't really explain these temperatures by just NLR, AGN illumination, and we can't describe this dust as a dust that had come from the torus. So our current picture is that we have dust in the narrow line region, and it is being heated by shocks, potentially down to these radio jets. Huda is now expanding this work to look at a larger sample. This is not yet out yet, this is in prep. But alongside ESO 428, she's now expanded this to look at the other objects in the sample which have clear extended emission, and looked at the lining up of where this extended emission is versus known shock regions from other literature. So we can see in ESO 428, we have a known shock region here where our extension is in the northwest. 4388 has a very well-known and documented shock region in the southwest. 3081 hints of a shock region in the north. And 5728 shocks at the edges of the cone are well-known and traces where we see our extensions. So that's some really exciting work, and is going into dust physics and dust survival and sputtering and all kinds of dusty things. And also has pushed for proposals to look at more physics around tying down the exact shock conditions. Are they fast shocks? Are they slow shocks? Et cetera, et cetera. So keep your eyes peeled for this work. I mentioned emission line contamination. Lucky me, I got that one to deal with. So we have images there in broadband filters. If you have mid-infrared emission in a broadband filter, it could be coming from the continuum, which could be dust, but it could also be coming from emission lines, which would not be dust, that would be ionized gas. So in an image, we don't have a spectrum, so we can't really disentangle what is emission lines and what is continuum directly. So in Huda's work, she proposed a method to estimate this using ancillary data from Symphony. So Symphony gives us spectra in the near infrared. It doesn't trace the exact contaminants that we want. For example, in the 10 micron filter, we have sulfur 4 as our main contaminant. Symphony doesn't cover sulfur 4, but Symphony does cover another high ionization, a similar ionization potential line, and maps it. So what we can do is take a map of a line with similar ionization potential and scale it to the flux that we measure from an unresolved observation, such as from Spitzer. And that way we've created sort of an estimated map of where we think our contamination is, and we can then subtract that. So what I've done is I've expanded Huda's work on ESO 428. Our sample of 8 galaxies also has 3 galaxies which are observed with MRS as well. What that allows us to do is measure the actual contamination with MRS, and we can then compare how we can quantify that and mitigate for that, but then we can also test how well this estimation method is working and see whether we can trust what we're measuring from imaging alone. And turns out it works reasonably well. So in the paper I'm working on, we have our Ideal way to do this would be by combining our imaging with our MRS, which we can do for 3 objects. In the top row here, we're doing it for NGC 3081. And we can see here is our Miri image, PSF subtracted. We can then make our line-only map from the MRS, and then we can subtract it to create a decontaminated map, which is what shows us continuum only. And then we have our contamination, which in some regions, sort of 30–40% heading up to in the outer regions here. If we have just MRS, we can do our PSF subtraction and we can arrive at similar conclusions, albeit PSF subtraction is quite hard, so there are some over subtractions in there. And then if we had only imaging and we were trying to estimate it using Symphony, and we create our mock line map from Symphony, that's estimated, and then we retrieve similar results here and similar estimations. It's not perfect, but in terms of the science case of looking at which parts of the structure are real and which parts of the structure are down to contamination, we arrive at very similar conclusions. Looking at it more quantitatively, this is radial maps of the contamination in the ionization cone with the 3 different methods, and they are largely in agreement in most parts with overestimates in the estimated method. So if the science case of looking for an extension, if we overestimate the contamination and the extension is still there, that means that extension is definitely there. So an overestimation for our science case isn't the biggest problem in the world. So what we found in this study is that emission line contamination is important, and more specifically, it varies greatly between objects. So if you are using broadband imaging for mid-infrared purposes, you'd have to treat it. And you can't just say, oh, it's about 10% in every galaxy. It's not 10% in every galaxy. It's not even able to average it spaxel by spaxel. It varies over the structure. It varies over object to object. So you really have to actually treat it. You can't just sweep it under the rug. We also found that ideally we would combine the 2 data sets, but with MRS, you can do it. You can do it reasonably well as well. And with if you only have imaging and you have ancillary data, you can make that estimate. So it's not, all is not lost. Moving on from there, once we have our contamination treated images, so we have in theory continuum only MIR images, we can then move on to characterizing the dust in there. And this is what Enrique Lopez Rodriguez, also in the room, is working on at the moment. So we can take our line-free Miri images along with the MRS and explore the properties of the dust. And what we find is that using a spatial correlation indicator, get this right, the line image is correlated with the total MIR emission, but specifically the continuum MIR emission is not spatially correlated with the line emission. So the dust is distributed not entirely throughout the NIR, but the NLR, but is distributed in shock regions or molecular clouds. We also find that the line contamination is correlated with the outflow rate and the outflow kinetic energy. And we find similar dust temperatures and properties across objects. So temperatures about 130 Kelvin, masses 700-ish solar masses, and similar emissivities across the sample. So there's more work required to see what processes are happening in these dusty regions, but our data places us perfectly to tie down this dust, the processes that are taking place, and what leads to the dust being there in the first place and the effects that it has on the surrounding region. So we look forward to finally working out exactly what's all going on there, tying everything together. And I think that's the real strength of GATOS is our multi-wavelength data and our depth of experience across wavelength regimes. And you can see this really well in the work that John Schneider is working on, combining multi-wavelength data to look at our Torus models. So Ismail already mentioned that the Torus models that Amira has worked on using the MRS data, we find that quite a lot of them can't be fit by the existing models. So John has been working just on one galaxy, on NGC 4388, with this extension up here, and specifically this knot to the southwest, and has been looking just at the unresolved nuclear region and creating SEDs, photometric SEDs, to try and fit with some AGN Torus models. So in those models, we have a component for the stars, a component for the AGN, and a dust model. And what we're doing is we're keeping the stars and dust, the models themselves constant. They're fit differently each time, but the same models. And then we're swapping in and testing 3 different Torus models. So we have Clumpy, we have Skirter, we have Cat 3D Wind. If you want to know more about those, I think there are experts in the room, so it's the perfect time to ask questions, but I'm not going to go into detail. By no means an expert on these. But what we find is our multi-wavelength data allows us really to push forward in terms of how much detail we can put into these models. We have existing HST data from Hubble, we have JWST data from MIRI, we have ALMA data. We've got 8 photometric points from 0.4 to 870 microns. That's a massive amount to cover. And when John does the best fitting model we can do, it looks like this. But importantly, when John compares the parameter space that is accessible to all 3 models, our ALMA point, so way over here in, where's ALMA? I've suddenly forgotten. Not mid-infrared. Radio. Yeah, millimeter. There we go. That's the word I'm looking for. Thanks. It's not currently covered by any of the models that exist. So we're again finding that the models that exist cannot quite describe the torus in the depth that we're looking for and what we're observing. So from our imaging, just our one imaging proposal with our sample, we've got this wealth of results already and more in the pipeline. We've shown that our extended MIR emission is explainable by dust that has been potentially heated by shocks. We've looked at the properties of this dust. We've developed novel methods for PSF subtraction and deconvolution, and novel methods for emission line contamination mitigation. And we've also tested our torus models and all kinds of data, all kinds of work that's going to come from this. So looking at GATOS as a whole, everything that Ismail said and everything that I said, we've learned a lot so far. The data is really rich. We're getting more and more information with every single micron that's covered. Our H2, warm phase molecular gas, we've got shock tracers, our PAHs are tracing AGN feedback, our dust grains. We're learning more and more about how complex dust is in our systems. We're looking at the things I just said around imaging. Here are all our results, and this is only from cycle 1. You saw at the start that we've had almost 160 hours of JWST time. So there's a lot more coming. I'll leave that there. Thank you very much. No problem.
Thank you so much. Sorry, it took a bit longer than it should, probably because of me. So if there is any question.
This is more a sort of a technical question concerning the PSF deconvolution and the PSF subtraction. So I have 2 questions concerning that. The first one is the PSF. I understand that you built your own PSF for the James Webb, right? So, but have you considered to build your own just in and check?
Yeah. That's beyond what yes. I think I'm going to default to David on that question. He is the expert.
Sorry.
Yeah, we looked into this in great detail in the master's thesis. So we compared empirical PSFs, model PSFs, and the most important thing is often that you have to fold in the fact that it's dithered. So reconstruction error is a major source of uncertainty as well. All of that has been considered. The model PSFs are really good as long as you do the reconstruction error properly. But they're still not perfect. There are elements that had to vary, like Gaussian jitter and so on, to optimize it. So it is a tricky process. It can't be done automatically. It only matters for these super bright things, right? If you're trying to just do like photometry, rough photometry or something like that, then it's okay.
Hi, thanks for all the talks. You're brilliant, brilliant work. I was wondering about this last sample. What's the luminosity? You mentioned that all of them are in the same luminosity class, right? They are all similar luminosity. I am assuming they are pretty bright sources, right? They are up there in the, let's say, luminosity sequence, whatever. So I was wondering if there's any plan to vary that in a sense. So if dust is so important for these sources, do you expect the same to be this should be the case for, I don't know, more like liner type of system, so like lower luminosity ones and so on? Do you have any plans for that? Yeah.
Do we have any plans for that?
Yeah, like if one of the cycles you are one of the future data you will plan to tackle that and so on. I think
indeed we have some proposals that are targeting some low luminosity AGNs. So these are work that is leading Lulu, indeed, that is in the audience as well. So we have some data for low luminosity AGN, but still data is coming. So, and we are planning to explore synergies. Well, it was in the conclusion, synergies with the low luminosity, but also with the high luminosity, no? Because it's complementary. You need to have all the luminosity range to understand.
Yeah, exactly. So I was just wondering, like, how dependent on this parameter, for example, this contribution would be.
So this is exactly what we are missing now. No? So we are doing individual works, but we need to do like a large sample to see what is going on with the. Yeah, it's excellent question. Yeah.
Thank you.
Thank you. Amazing presentation, amazing work that you are doing. It's just a curiosity, but they found a difference then in the outflows that they found, for example, the ionized outflows that they measure from the optical ones. They were able, because I suppose the obscuration is much lower, but that is more or less how much difference they found, for example, in most outflow rates or something like that. I can check in the paper too, because, but...
The main difference here, as you said, is obscuration. So so the measurement of the outflow rate are different, but I guess that probably Lulu is the best one to answer this question. So you can pass the.
I think here that the most different two sources are the two with the lowest outflow rates measured for the optical one, and I think the main reason, at least according to our measurements, is due to the attenuation. I mean, because the infrared observation is more kind of immune to the dust extinction, so we derive the higher outflow rates compared to the optical one. Yeah, you can see for the two data points in the most left part.
Thank you, everyone. Maybe very basic because I'm not familiar with the field, but when you are talking about the pH molecules, if I'm not mistaken, I remember that was the molecule that we could also find in the ISM. But I assume that you are focused on the center and you have a data cube or based on the size and whatever that's related to the AGN, and it's not come from other sources in the galaxy.
So the thing is that when ones have a look to the diffuse emission or the star forming regions, what we found is practically the same path profile. So we have like a pattern plate. So you can see the green area there is the average of all these spectra. So they are extremely similar. So once you go close to the AGN, is when you start to see differences, no? The same happens in the local universe. When you go very close to a star or a PDR or something like that, you start seeing these differences. So something is making these changes in the population. We are cross-correlating this with the outflows, with the different regions. And we are making the assumption that this is because of the AGN, because they are co-spatial. No? So this should be happening. No? The question that is still open is if these are exactly in the same phase, because if they are kinematically connected, and we have also the other works looking at the kinematics of the pHs, and is confirming this. No? So yeah.
I would like to thank Ismael and Steph for giving this amazing presentation. And I would also tell the audience that this week we have this bunch of experts on James Webb observations and AGN. So take the opportunity to ask any questions that you may have, because I mean, we really, the learning curve, no? When you work with the James Webb data, it's very steep, and we have been working on this for many years now, a couple of years now. So yeah, I mean, use us if you want. And thank you so much, guys, for doing this.
Thank you, GATOS.